Aiden, I'm not sure if I'm going to get through the whole lesson today. I'm going to spend 2 days and be throwing a lot of stuff at you talking about friction. But then the class after that, we're going to watch a Mythbusters video, a really nice example of friction and application. And we're also going to kind of press pause. So I'm going to be throwing a lot of homework at you. Don't panic. There will be some time for you to get it done in class as well. So what is friction? I had you all press your hands against your table and pull towards yourself. And you said, yeah, I can feel something tugging against you. What's going on there? There's still some debate as to whether or not this is actually what's happening. So I'm going to teach you the most commonly accepted model for friction. It might not be bang on. There may be something else going on there because this is at the subatomic level and it's really hard to take a picture. We think that friction is due to the interlocking of molecular hills and valleys between a surface and an object sitting on the surface. So even though your lab tables might appear smooth, on the atomic scale, when you zoom in, they are not. And so we think what your hand was feeling was on your hand there are microscopic hills and valleys, and on your table the same thing, and they were just rubbing past each other, kind of like rubbing 2 pieces of sandpaper along each other. The key idea is this. Friction resists sliding. That's the direction of friction. Ask, which way is this object sliding, or which way does this object want to slide? Friction's pointing in the opposite direction. And so because of that, it can resist motion, like when you're trying to slide the gym benches across the floor. It can also create motion. Friction is what pushes you forward when you walk. So example 1 says, draw the direction of friction in each case. I'm going to zoom in. We're running into a bit of a problem here. I could not get the Word document, that box, to touch the surface. So if it looks like it's hovering, it's not. This is supposed to be completely filled in right here, and I just couldn't get it to mesh. Okay? Which way is this block sliding, Cohen? Be obvious. To the, looking for where it starts. Which way would friction be pointing then? Friction here would be pointing to the left. My abbrev for friction is an F with an FR. I don't know why I put the R there. Any textbook puts an F with a subscripted F. This may be the only time ever that I put an extra unnecessary letter, that I do more writing, but it's a habit that I just can't break, so I've stopped trying. What about for a car speeding up? Well, if we zoom in, the tires are trying to push backwards against the road. Forces come in. If the tire pushes backwards against the road pushes forwards on the car, and that force is friction. Here, friction is pointing forwards. This is why I said to you earlier, on a car, it's not a car. It's not an engine that makes a car go forwards. It's not even the tires that make a car go forwards. It's friction. This is why you can't drive on ice. No friction on ice, you're going to have a tough time getting that reactive third law force. And again, you can see it's resisting the sliding. The tire tries to slide backwards. Friction pushes the car forwards. Ooh, what about when you tap on the brakes? When you tap on the brakes, what really happens is your tires try and apply a forwards force against the road. Forces come in. The road pushes backwards on the tires, and since the tires are attached to the car also feels that force. What force is that? That's also friction. How do we calculate friction? Well, it's still sort of based on MA, but there's other things that are going to affect it. The first thing is some objects are slippery, some objects are sticky. We should have some indication of the stickiness or the slipperiness of an object in our equation, and we do. If you go to the next page over, I wrote here, the amount of friction depends on The types of surfaces that are in contact and how slippery or sticky they are. We have a symbol for stickiness or slipperiness. First of all, it's called the coefficient of friction. Now, the coefficient of friction is not a force. It's just a number. It's a ratio. Closer to 1 means really sticky. Closer to 0 means really slippery. And the Greek symbol that we use for it is the Greek letter mu. It looks like this. You've seen it before because it's also used as a metric prefix for micro. We just don't have enough letters, even if we start including Greek. We need more. We're having to reuse some of them, Zaina. Sorry, but we just are. Newton's is N. North is also N. Some textbooks use capital N for normal force as well. I refuse to do that. I use F with a subscripted N because that's enough. So if you're looking in the notes here, the symbol, it looks like that. It's kind of like a lowercase handwritten U with a droopy tail in the front. It's where our letter M comes from in our English alphabet. There are all sorts of jokes that go with this. What does a Greek cat say? Mew. What does a Greek cow say? Mew, right? There's all sorts of dumb jokes that way. So this is the symbol for stickiness. The smaller that number, the slipperier. The higher that number, the stickier. And if that number is bigger than 1, that's glue. It can hold its own mass and more than its own mass. So steel on ice has a coefficient of friction of about 0.01. And rubber on concrete tires have a coefficient of friction of about 0.75. They're pretty sticky. What else does friction depend on? I'd like you to imagine you're sliding something across the gym floor. If it's heavier, do you need to push harder or lighter? Be obvious. If you're sliding harder, and so maybe the force of gravity should be in the equation, except I also want to take into account that if I'm pushing something heavy, if I lift up, it gets way easier to slide. So I'm still feeling friction, but it gets way easier to slide. What force am I changing when I lift up? Not mg. What? Normal force. Friction depends on two things. It depends on how slippery, mu, and it depends on the normal force. This is the equation for friction. Friction is mu times the normal force. Is that on your formula sheet? Is that on your formula sheet? Should be on the same row as F equals ma, and it should be on the same row as weight. In fact, I think it's the last one on that row. That's why I told you this is the last new force you're going to learn. You don't need to memorize it. You probably want to because you're going to get sick of looking it up and it's not that hard. Friction is mu times the normal force. Okay. Mu is the coefficient of friction. It has no units. The normal force is newtons. Friction is newtons. So yeah, this has no units. Okay. Example 2. Suppose we were pulling a 6.5 kilogram mass across a rough surface at a constant speed. I would probably mentally underline the phrase constant speed. That tells me an awful lot. How hard do we need to pull? Okay. What's this question want me to find? Ella, what's this question want me to find? A force. And I think the fact that they gave me a coefficient of friction means there's also friction. Is there more than one force in this question? This is a job for a free body diagram. Although, did they give me a picture? I'm going to be lazy and label the picture. Okay, here we go. What are the forces acting on this? Get the obvious one. Is this box sinking into the ground like quicksand? Is it flying here like Superman? So there's another force the same size pointing up. We used to call it the ground, but we've generalized. What are we calling that mystery force that a surface exerts when an object pushes down on it? Okay, that's the normal force right there. Okay. What else? Well, this question is asking how hard we need to pull. This is a mystery force coming from off the page. We're going to use a generic term for that. We're going to call it F applied, except I'm not going to write the F, I'm going to write F-A-P-P. That's the applied force. And what I mean by that is something's pulling from off the page. It could be a person, it could be a machine, it could be invisible leprechauns. I don't care. All I know is that's the mystery force they want us to find. What else? Yes. Which way is this block trying to slide? To the? Which way is friction pointing? To the? Because friction resists sliding. I'm also going to assume that it's losing. If it wasn't losing, this thing would not be accelerating, and I doubt they'd ask that. Vertically, my forces, Ella, are balanced. Horizontally, who's winning? Which one has the bigger arrow? F applied. Who's losing? Equals. What does winner minus loser always equal? What? MA. Yeah, don't look like, no, this is our setup. This is why I told you, I cannot give you all the equations. You're going to get winner minus loser equals MA. I'll give you friction. Friction is mu times the normal force. The rest we'll have to derive from scratch. So this situation, it looks like it's F applied minus friction equals MA. We could start plugging numbers. No. What's this asking us to find? In my equation, what's it asking me to find then? Which one of those is the mystery force coming from off the page? That's how hard we're having to pull. F applied. Okay. How will I get the F applied by itself? How will I move that friction over? Yep. So my next line, I would say F applied equals MA plus friction. Now I'm going to substitute my new equation for friction in. Friction is what times what? Mu times the normal force. So my next line, I'm going to move to here, is going to be MA plus mu times the normal force. Eric, you okay with what we've done so far? By the way, as you get good, you'll start to take some shortcuts and combine steps. I'm doing every little thought process here. Ella, let's do a check. Do I know M, the mass? Did they tell me the mass in kilograms? Do I know A? Oh, constant speed. What's A exactly as a number? Well, that's bonus. I probably could have spotted that earlier. I might have been able to start out simply by saying, you know what? It's a tie. F applied equals friction. In fact, technically, those two arrows should be the same. Okay. Do I know mu? What's mu? Hey, what's mu with you? No, what's mu? Okay, I know that. Problem. I don't know the normal force. Oh, but look. I don't know the force exactly the same size as the normal force. Which force is exactly the same size as the normal force? So I can say, how big is F applied? It's going to be the same as mu mg in this case. That was a lot of reasoning that we just did there for this one question. Hopefully not too much. What's mu? I don't know what's mu with you. What's mu, Emma? What's M? G? 9.8. How hard do we need to pull to keep this mass moving at a constant speed? 0.64 times 6.5 times 9.8. We need to pull with 40.768 newtons. I'll call it 40.8. Is that all right? Okay. Next page. Am I right? Is that correct, or did I make a typo? I see people look. I'm good? Okay. I didn't do that one in my head, so who knows. So I wrote here, note, we give a special name to an unknown force appearing from an outside source off the page. We call it the applied force, symbol F up for F applied. In fact, they'll often say something like, a force is applied to, or how big a force must be applied. So they'll actually often use the word apply to describe it. Not always, but pretty often. And that's, again, don't overcomplicate it, Scott. It's just the mystery force coming from off the page that you want to find. Example 3. Suppose we are pulling on a 6.5 kilogram mass across a rough surface with an applied force of 86 newtons. What's the acceleration of the mass? Ooh, Eric, what's this want me to find? Do you see a VI, a VF, or a T, or a D here? No. You know what? I think we're going to use Scott's theorem. We're going to use forces, and we'll divide by m. So this is a job for a free body diagram. Shall we put all that together? What are the forces acting on this? Get the obvious one. Good. Is this box sinking into the ground like quicksand? Sure no. Is it flying through like Superman? Sure no. So vertically the forces are balanced. There's an arrow pointing straight up, the same size as gravity. What force is that? That's what we've called the normal force. The ground, the surface pushing back up. What else? The question mentions one. It says with an what force of 86? What do we call, which force is that? Which force is that? Applied force. Okay, and that's going to be to the right, so I'll put it here. F applied. What else? Well, they gave me a coefficient of friction. That's their way of saying include friction. Which way is this block accelerating and sliding? To the right, so which way is friction going to be pointing? To the good. Who's winning? Good. Who's losing? Equals always what? MA. Don't overcomplicate it. Winner minus loser equals MA. That's our equation. We're not anywhere near solving yet, but we can say winner, F applied, minus loser, friction, equals MA. There's my setup. Eric, what's this asking me to find? Acceleration. How would I get the A by itself? Scott's theorem. Elaborate on that. How would I get the A by itself? Yep. Divide. No, not divide. Divide the M over. Boom. Yeah. Yeah. You were saying it backwards. We always do that. It's partly because English and math are backwards language. They are. 5 less than 3 is 3 take away 5, even though you said the 5 first, right? Okay, let's see what we can plug in here. I guess A is going to be, we're not going to go numbers yet. F applied minus, what's our equation for friction? It's on your green sheet. It's also on the previous page, or you might have memorized it already. Friction is what times what? Friction is what times what? Mu times the normal force. Find where that is on your sheet so you know where it is, okay? It's right next to F equals MA, F net equals MA, and then there's that thing about weight, and then next to that I think it says FR equals mu times the normal force. And then divide by M. Eric, do I know the applied force? Do I know the applied force? Oh, yeah. What? Good. Hey, what's mu? I don't know. What's mu with you? Do I know mu? Yeah. Do I know M? I don't know the normal force. Oh, but look, 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 look. I don't know the force the same size as a normal force. Which one? Can you go, what? Read me those two letters. Yeah. Okay. So I can say A equals F applied minus mu mg. Now, right around now, someone says, Mr. Duick, why don't you just say that friction is mu mg? It's not, and I'll snap if you ever say that. Right now, friction is equal to mu mg because right now the normal force is equal to mg because right now I'm doing boring questions with you. But the normal force is not always equal to mg when we get into more interesting stuff. Okay? But Eric, I think now we can plug and chug. What did you say F applied was? 86? Yeah. What's mu? I don't know. What's mu with you? 0.64? M, 6.5. G, 9.8. All over. All of you should try typing that into your calculator. Is this a fraction? Yeah. Is there more than one thing on the top? Definitely brackets around the top. Don't need to have brackets around the bottom. Only one thing on the bottom. I got 6.96 units. It's an acceleration. You know this. Thank you for not letting me down. I knew I could count on you. 6.96 meters per second squared. Okay. Example 4. Suppose we are pulling on a rough mass, on a rough surface with a force of 48 newtons. What's the acceleration? I'm going to skip example 4 because we just did it. It's very, very similar to example 3, except the applied force is a little bit smaller, but it's still going to accelerate. How do I know? Because if we pull with 40.8 newtons, that was 2 questions ago, that's enough for us to accelerate at a constant speed. So, as long as I'm pulling with more than that, this thing will accelerate. So I'm going to skip this, and I'm going to jump to example 5, a thought puzzle. It says this. A student gives an old shopping cart a big push on a flat, rough surface. So we're pushing it to the right. We give it a big push to the right. Which of the following, A, B, C, or D, is the best free body diagram for the shopping cart? Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. So look up. I don't have a shopping cart, but I do have a little office chair. What we're doing is we're giving it a push, and we're talking about the free body diagram after I let it go, but before it comes to a stop. So look up. We're talking about the free body diagram right now, but not after it's come to a stop. Once again, we're going to vote. Once again, how high we hold your hand up is how sure you are of the answer. Who says, Mr. Duick, this is easy? It's got to be A. It's A, easy. I got 1, 2, 2. B, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. C, no one. D, no one. You know what? Let's go with a bit of a process of elimination. Let's remember what free body diagrams mean. In D, which way is there an unbalanced force? To the Which way is there clearly an unbalanced force? To the right. Which way must this accelerate? This would be speeding up. Was it speeding up? No. What about here? Which way is there an unbalanced force? Nowhere. So how would this be traveling? Constant speed. What about here? Well, there's two possibilities. This arrow looks like it's a tiny bit longer than that arrow, which would mean it was speeding up, or maybe they're supposed to be the same. All I know is there's only one free body diagram that has an unbalanced force slowing down. Which is the only free body diagram that has an unbalanced force slowing down? Has to be. Has to be. Which law did I use to figure that out? Yeah, one of Newton's. Thank you, Captain Obvious. What? Pardon me? So since Fahim got that wrong, it's Newton's first. We can't write Newton's first, so we'll have to say only A has an unbalanced force, friction, slowing the cart down. Had Fahim said Newton's first, we could have written Newton's first, drop the mic, and walk off. But since he got it wrong, we'll write it out. Okay? Yeah, B can't be right. It's either speeding up or it's going at a constant speed. It's a little tough to tell whether the two horizontal arrows are meant to be the same size or whether one's longer. It's got to be A. Are you starting to see why I'm trying to tell you a good free body diagram and Newton's first tells you an awful lot? I like example 6, I like example 6, I like example 6. Example 6 is a nice question. A force of 12 newtons is required to keep a mass accelerating at 0.8 meters per second squared. What is the coefficient of friction between the mass and the floor? Ooh! Aiden, what's example 6 asking me to find? It's not asking me to find friction. Read carefully. What's it asking me to find? The coefficient of friction. You know what that is? Hey, what's mu? I don't know what's mu with you. It's asking me to find what's mu. Okay? The stickiness. Any suggestions on how we might want to start, Aiden, my friend? Find the... Before that, what might this be a good job for? There we go. Okay. Well, what are the forces acting on this? Get the obvious one. Good. What else? Are we sinking into the ground like quicksand, flying like Superman? So? Bigger, smaller, or the same size as gravity? When would it be different? Patience. We'll do some where it's different. What am I going to call that 12 newtons, that mystery force coming from off the page? Yeah, so I'm just going to put an arrow, and I'll put a little APP underneath the F right there. The 12 is already there. That'll catch my eye enough that I won't miss it. What else? Which way? I'm pretty sure this is sliding to the right, so friction is going to be pointing to the left. Let's write an equation. Who's winning? Who's the loser? Equals. Now, I often see kids panic here because they say, Mr. Dewick, this wants me to find mu, the coefficient of friction, and there isn't one yet. Wait a minute. Aiden, friction is what times what? So my next line, I would go F applied minus mu times the normal force. That equals ma. What did you say they're asking me to find? What's right in front of the mu that I don't like? Right in front of the mu that I don't like. What? I'm going to swappy dance. I'm going to swappy dance this whole thing to that side. Why would I deal with the negative if I don't have to? So I'm going to, first of all, erase this. There we go. So I'm going to move this to there, this to there. And Aiden, that's going to give me the F applied dropping down like a domino. Minus MA, that equals mu times the normal force. What am I trying to find? How would I get the mu? Oh, so you're saying I agree. Let's do a quick check. Do I know F applied? 12. Do I know M? 5. Do I know A? Oh, 0.8. Ooh, I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Ah, so my final line, before I start plugging numbers in, I can say mu equals F applied minus MA all over mg. F applied, 12. M, 5. A, 0.8 divided by 5 times 9.8. Again, I strongly encourage all of you to try typing this into your calculator so that you know how to type something like this. On mine, I think I'm going to have brackets around the top and around the bottom. Coefficients of friction are usually decimals between 0 and 1. 0.163? Is that right, or am I wrong? Yeah? Okay. So if you didn't get that, double check your typing or show me later. Units. Aiden, units. Mu is what we call this. What are the units? Now, I'm not surprised that you're not sure. Look up. Keep looking up. Keep looking up. What are the units for the coefficient of friction? It's a unitless ratio, but it doesn't have units of its own. It's just describing almost like a percentage, but it's not a percent, how sticky something is. So this is one of the few times, no units. One more, we're done. Suppose we're pulling an 8.5 kilogram mass across a rough surface with a force of 48 newtons. What's the acceleration? Okay. I can do this. Claudia, what's this asking me to find? Any suggestions on how we want to start out? This is a good job for a free body diagram, I think. Now, how did I put that together? I don't see a time or a VI or a VF. You know what? We're going to find acceleration by using Scott's theorem. We're going to write a force equation and then divide by m to get the A by itself. So what are the forces acting on this block? Let's get the obvious one. I totally agree. Keep going. So I always do, are we sinking into the ground like quicksand? Are we flying through like Superman? So, same size. What force is that? Normal force. Right? What else? Well, I think we have this force. We're pulling, you know what? This is the applied force. What else? Do they want me to include friction? How do I know if they give me a coefficient of friction either in the question or on the picture? And the fact that it said rough surface. So I'll draw friction that way. Who's winning? Who's losing? Equals? Okay. What are we trying to find? Let's use Scott's theorem. I guess A is going to be F applied minus friction is what times what? Mu times the normal force all over M. I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force. Which force from my free body diagram has to be the same size as the normal force? Yeah. So I can say this will be the same as F applied minus mu mg over m. So let's plug in numbers. What was F applied? It's going to be easier to find it on your question. I think I might have scrolled. Oh, no, there it is. 48, right? Minus, hey, what's mu? I don't know. What's mu with you? What's mu? 0.64. M, 8.5. G, 9.8. All over 8.5. I think when you type this in, you're going to get a bit of a weird answer. What's weird about your answer? What? It's negative. Is that correct? You get negative? Got a negative? So here's what that means. If you're ever solving for acceleration and you got a negative, it means you picked the wrong winner. You get a negative quote, you're still typing. Once you're done typing, then look up. The nice thing is, it's a really easy fix. So on my calculator, if I type this really, really quickly, I get bracket 48 minus 0.64 times 8.5 times 9.8, close off the bracket, divided by 8.5, and what the? Okay. You get negative 0.625? Put your calculators down, look up. Claudia, you picked the wrong winner. Who's actually winning here? Friction. This is the winner. This is the loser. Look up, look up, look up, look up. Watch. I'm going to do my changes in red. Winner, loser. Look up, keep looking up. Winner, loser. Winner, loser. Winner, loser. It's a pretty quick change. Make your winners losers and your losers winners. And even better yet, on my calculator, I can just backspace, and if I change the minus sign to a plus sign, and if I insert a negative in front of the 4, I'm good. Now, in this case, I got exactly the same answer, but positive. That won't always be the case as we get to more and more complicated questions. So you can't just say, I'm going to ignore the negative and make it positive. Eric, you will have to change your winners into losers and your losers into winners. And in particular, for a really complicated question, you might find, oh, I thought it was sliding to the right. It's sliding to the left. I got friction pointing the wrong way. You might actually need to scribble out friction having it pointing in the other direction. We'll get to those. But for now, Clody, if you get a negative acceleration, what does it tell you? Pick the wrong winner, go fix it. And it's a pretty easy fix. 0.643. What does this answer tell us about the motion of the object? First of all, it does say that we're moving this object to the right. But which way is it accelerating? Left. So how is this object moving? If it's moving to the right but accelerating to the left, it must be what? Slowing down. Oh, that's allowed. Yeah. I'll come look at your calculator in a second. But first of all, this object must be slowing down. Am I right? Is it 0.643? No. Oh, I'm wrong. So I made a typo. Where did I make my typo? 0.64 times 8.5 times... I wrote it wrong? 0.645. Can I not even read my own writing? Why am I missing that 2 for some reason? 0.625. Is that better? Maddie, is that what you're trying to say? Okay, sorry about that. So I got the right answer on my calculator. I just copied it down wrong. That's a little silly. Okay. This object is slowing down. If they ask for a direction, the acceleration is to the left. It must be. So that's an introduction to friction. Friction is what times what? It's mu times the normal force. What's mu? Stickiness. It's a ratio. It has no units. Closer to 0, slippery. Closer to 1, good grip, good traction. I don't know the normal force. Oh, but look. From my free body diagram, I'll know another force the same size as the normal force. I'll be able to figure out the normal force. One is good. Two is good. 3 is good. 4 is good. 5 is good. Putting a star next to number 6, but yeah, I'm assigning it. Putting a star next to number 7, but yeah, I'm assigning it. Those are tricky. They're so easy that it's tough. 8 is good. 9 is good. Yeah, I signed all of them. 10 is good. Now, there's only 5 minutes left in class, so this is why I said a couple of days from now I'm going to be pressing pause. But I have a feeling in tomorrow's lesson I'll probably do something similar to 6, 7, 8, and for that matter, 9.